I can do it.
Awesome. Cool. Welcome, everyone. This is another fun adventure with Deep Learning Adventures. We're joined by many friends all around the country today. If you're joining us from YouTube, welcome. Hope you're enjoying the sessions. Feel free to comment and share your experience with us. I'm joined by my great friends, David, Robert, and Dmitri today. And Dimitri's, I want to thank him again for leading this transformer and attention session. This is our part 2 session on attention and transformers. We learned a lot last week, and we're looking forward to this session as well. Let me just share some notes with you, some housekeeping notes. Again, this is the meetup page for part 2. We have some links here if you want to check them out, including a notebook that Dmitri will cover soon. We have our own links for this new attention playlist as well. Hopefully find it interesting, as well as some other resources that we'll cover during this session. Cool. I will stop sharing here. And again, thank you for joining us, and pass it to Dmitri. Thanks again, Dmitri, for leading this session.
Yeah, absolutely. So let me, could you enable participant screen sharing?
Absolutely. There you go.
Yep. So this session, actually, I had, yeah, there it is. I had not finished the transformer session last time, so this was the plan, just to finish whatever we have left from the session 1, and then go over BERT, which is I would say fundamental model built in NLP in the last 3 years. One of the groundbreaking papers that gave rise to all kinds of many kinds of follow-up models and follow-up structures, and so that was a really important paper. So we will go through the paper itself, through the research article, and then we'll look at one of the implementations in the TensorFlow tutorial, which will be classifying IMDb movie reviews with BERT. So let's finish the session 1. So to remind, we started with this notebook, so which implements the classical encoder-decoder architecture, which is this one. So the transformer having both the encoder part, which encodes the input Portuguese in our case into some sort of hidden representation, and then the decoder part, which looks at the already encoded part and translated sentence so far and decodes it, one token at a time. So this is what the decoder is doing. And we looked at a specific implementation of this, the 3 arrow shape here, which is the multi-head attention, which can be either looking at itself. This is called the self-attention, right? Basically understanding which parts are important for me to interpret myself correctly, which is present both in the encoder and the decoder. And then this is the cross attention part, which is basically the English translation querying the Portuguese input to understand, which Portuguese tokens in the input are most relevant for me to generate the next translated token. So these are the 2 types of attention, so self-attention and cross-attention. So we looked at that and at how they implemented. So the rest of the notebook is actually quite simple. They basically, once we have these building blocks of attention, everything else is pretty straightforward. The residual connection, the feed-forward part, and the layer normalization. So all of this is relatively straightforward. So what they do is they implement this encoder as a layer, as a keras layer object, which basically implements whatever we discussed right now. So, it has the multi-head attention and the feed forward part, and then that is abstracted as a keras layer to be repeated n times. So that's very easy. The same with the decoder. So once we build the multi-head attention, both for the self-attention part and the cross-attention part, all we have to do is package this as a keras layer, and then we can repeat it, arbitrary number of times. If I'm not mistaken, they repeat it 6 times, each of the encoder and decoder layer. And finally, yes, so the encoder would implement the layer n times, so 6 times, and also add the positional embedding, positional coding, and the input embedding, meaning the Portuguese words embedded into the model, the space of the model. So this would be a fairly simple implementation. Both the encoder and decoder are ready, and then they package this into the transformer itself. And so the transformer would have both the encoder and the decoder parts, and they implement this as a keras model subclass. So each one would actually each transformer object would actually build the entire computational graph from the input Portuguese sequence up to the translated English output, and then so that this entire computational graph is able to then calculate the loss, which will be driven by the actual ground truth English translation, and then all the gradients will flow through the computational graph and update the weights. So in this fashion, it's no different from any other model object in TensorFlow. Yeah, we would call this, we build the transformer with a specific number of layers, and all of these parameters are tunable. So we could actually, pick and choose depending on the task and the complexity of the task. And so, we will talk a little about this hyperparameter optimization when we get to our 3rd session in December, when we will cover the application of this classical architecture to a non-NLP task. But this seems to be pretty standard, particularly the model. So the internal dimension of the model is generally either 512 or 1024 or somewhere in between. But those are the two extremes. Generally speaking, the number of heads, sometimes people use 4. In this case, they use 8. So this is a generally fairly typical structure. And then what I was gonna focus on is the training procedure itself, which they use. Yeah, here we are. So we could actually take this transformer model object and train using just .fit, and then have a history, and it's basically subclassed from the model, so it will work exactly the same way. There is nothing wrong with that, except for it will probably take days instead of just hours. So that is a fairly legitimate, but not very optimal way of training these types of large models. Now, what TensorFlow has is a special object called GradientTape. Now, maybe they use this GradientTape object in some other notebooks, but this is one place that I think is basically deserves going that deep, because GradientTape is the lowest possible level you can get in training a TensorFlow model. So what it does is basically defines you have to define your loss object, and then for each step you calculate your loss, which is driven by comparison of the model output and the ground truth, and then the gradients will have to be like explicitly called from the optimizer to have these gradients, basically flow through the loss object, and so update all the trainable parameters of your model. And so let's just spend a couple minutes going through this architecture. So first of all, we need this decorator tf.function, which what it's doing is basically converting the entire computational graph into a computational graph in TF1 sense, which is basically a predefined steps and predefined architecture to transform your inputs into the outputs, which in TF2 was sort of released. You can still go graph-like, or you can do eager evaluation as in TF2. But if we think about the efficiency and the latency, we should go with the graph-like object, because what it does is, as they explain here, it trace compiles the training step. I'm not exactly sure how it works on the machine code level, but essentially this is mapping exactly all the transformations, all the computations you're doing, mapping and building this computational graph once and for all, and so without changing that. And so it's really important to make sure the shapes of the inputs and the shapes of the outputs, once you freeze it in the computational graph, everything works very fast. And I've tried both with TF function and without for the challenge I mentioned, and so the difference is like more than an order of magnitude. So whenever you can, and whenever the latency and the efficiency is the issue, TF function is the way to go. So basically what they do is they create the input, and this is the target, real is the ground truth. So the first semicolon is the batch dimension, of course, and then the this one is the ground truth. I guess for the so let's step back and let me show you how the target. Yeah, so this is the targets. So the real target is a lion in the jungle is sleeping, end of sentence. And so we hope that the Portuguese input is translated into this. So this is the ground truth. Now the input of the target is the same thing shifted one token to the right. This is called teacher forcing, right? So basically we feed into our transformer, into our decoder, we feed the actual output as opposed to what we predicted. And so teacher training, teacher forcing is frequently used, especially in text generation, in machine translation contexts. And so what we have is we define this input and the ground truth, and then we build this object, which is, with TF gradient tape as tape, we call our transformer model that we created on the input and the target input, and we mention training is true, so that all the weights could be updated. And then we basically, once we generated the predictions, we can calculate the loss. So this is the central element of this GradientTape function call. So being able to calculate the loss from a predetermined loss function. Everything else is fairly simple. So then you, on this tape object, you call the gradients are tape.gradients, and then you mention that you want to update all of your trainable variables into the transformer. So this is the syntax they have. And then whatever optimizer you have, which is also a TF optimizer's object, for example, Atom, you optimizer.apply gradients. And so you zip the gradients that you just calculated with the variables. And so basically, when we call a model.fit in a like a simple API, this is doing exactly that. All of this is actually happening under the hood. It's just abstracted away for us to be able to use the keras in a couple of lines. But actually, this is what's going on. Now, this tool doesn't, they're optional. This is these are metric objects that accumulate the loss and the accuracy, so they don't enter the gradient tape logic directly. But these two, I thought, it's just interesting to see how it works. And then the training itself is just looping through the epochs, and then for each step we actually go, so this is what we call, right? So for each batch we call the training step, which we just defined here. So we call the training step on the inputs and the targets. And so this is the outer loop of the training that goes through all of the examples and maybe multiple times depending on the number of epochs. So those were the two sort of quick comments that I was going to make on the transformer itself. And let me know if there are any questions on this one before we go into onto BERT.
Go ahead, Robert. I'll go for you.
Oh, okay. Yeah, this is pretty cool. I was wondering if there's a way to use this infrastructure to use dropout on training as well. I'm assuming this is not using dropout.
Yeah, of course. So you could basically within this training step, you could do anything. Like, for example, you could define a specific checkpoints outside of your TensorFlow checkpoints, like specifically, after each 10 batch, do this, right? And then, so, any type of action or function call that you would imagine doable in TensorFlow, you could insert it directly here into the train step function. This part is less flexible because, as I said, it has to be sort of converted into computational graph. So I'm not exactly sure whether you can do like flexible dropouts, etc. here, but here definitely yes.
Yeah, I was just thinking you would want to put some sort of a mask on where you're applying only certain gradients. Well, yeah.
You mean here?
Yeah, where you're zeroing out some of the neurons and then only calculating a subset of the gradients in a particular step.
It's probably possible to do. I haven't seen it, but probably you could be doing that because there is a masking going on here already, right? So in this step, when you call the transformer on the inputs and you generate predictions, so transformer is ingesting the masks or generating and applying the masks. So maybe it can be called not all the time, like every 10th time or something. But yeah, I wouldn't inject like arbitrary logic here, but you could do anything you want here in this the training loop itself. So
but I appreciate seeing how to build one of these things kind of from scratch.
Yeah, that's a good methodology. Dmitri, quick question. So I see in the training that the input is Portuguese, but the target is English. But you mentioned this teacher forcing process earlier. When exactly is that used? Is that used under the hood, or is that used as a separate process? I didn't understand that.
The inputs to the transformer is the Portuguese input and some English translation, right? So the English translation is shifted one token to the right, and then just if we forget about the training itself, just how does it work? So we let's get back to the picture. Okay, yeah, so we have the inputs and we have the outputs. So it's just the outputs are shifted one to the right, and then the task is to predict from the inputs and the shifted outputs the true outputs, which must be shifted one to the left. So this is what we understand by teacher forcing, right? So it's basically when we predict the first token, it may be wrong because the shifted to the right first token is usually a placeholder, like beginning of the sentence, and then you have to predict the. But then we know that, for example, the correct first word is not the, is a, right? And then we feed the a into the model, not the that you predicted, but the correct, the ground truth. And so each output token is generated with the actual ground truth preceding it, not the ground truth, not the predictions that you generated that preceded the token, but the actual preceding sequence. So that is the teacher forcing.
Right. And have you seen this in other contexts, or is that a transformer innovation?
No. It's used in. I might be wrong, but I guess they use it in the previous generating things too. Yeah. So
like a popular NLP methodology, I assume.
Yeah.
Okay, cool.
So
thank you.
For generation only, yeah.
Dmitri, I had a quick question about the part where they're using the gradient tape. If you can go to that code.
Sure.
Yeah, it's in that training and checkpointing. It's down there. Yeah, right there. So I didn't quite understand, like they are using with here for the tape, right? So it manages the resources and stuff, so you don't have to close things.
Yeah.
But then the tape isn't used until outside of the with statement. So what's really going on there? Why are they using with? You see the indentation there?
Yeah.
I would have thought it would be inside the indentation. That's not like when you use with like a file, you do all your file operations within the with, right? And then when you come out of the with, it manages all the closing of the resources.
Yeah.
But so I don't understand why they use tape outside of that.
That's a good question. So I guess I don't know exactly how this context manager works. I guess this is the way I read it. This is just the description of a single atomic training step that is happening over there. So I'm not sure what exactly this context manager manages. Is basically once you run this tape object has the dependence of the loss with respect to the weights, and so that I guess my guess would be this with the context manager make sure that the loss is actually sort of having, or somehow taking into account the dependence with the trainable weights. And so, but I don't know the specifics of why they
Okay.
have it here.
It looks like it's writing it into the tape there, right? So that it's stored in that tape by the time you're calling it once you're done. It's like a stream that it's writing it to.
I would also expect this to be inside the context manager, so I don't know why they have it outside.
All right.
Okay, then.
Awesome.
So should we move into BERT?
Yeah, that was the last part, right? Is there anything else here, Dmitri? No, maybe comparison.
No, actually, then they try translating, actually running the inference.
Okay.
And yeah, so but there is nothing interesting here.
And some attention plots. Okay.
Apart from the different ways you can decode your outputs. And so, I mean, but that is more like into the NLP depths. Like you could decode it greedily and just take the most probable token all the time, or you could do something more flexible, or increasing the temperature, as they would say, right? So do, like, for example, calculate a few tokens ahead and then choose something else. But that is not inside the transformer logic. This is outside of that.
Is that referring to like beam search, like a methodology to pick?
Yeah, you could do beam search. Yeah, you could do beam
sentence?
search.
Okay.
Yeah.
Cool. Thank you.
All right. So let me close this, and yeah. So our next section here would be to talk about BERT. So I had yeah, I had this thing. So I thought it would be interesting for us to see BERT in context with the other transformers. And so BERT came out in late 2018, I think 3 years ago. The paper was renewed in 2019, so sometimes it's 19, 18, so it's around 2.5-3 years old. And these are the number of parameters, like the billion of parameters. And so BERT's base is 110 million parameters. It's right here. And so BERT large is 340. So we'll discuss both of them today. So it's right there. But it's interesting how they keep not just doubling, but this is logarithmic scale. So how they keep increasing the scale logarithmically over the past 3 years. So the GPT-2 with 1 billion parameters seem to be like a really giant thing. And many of us would remember this wonderful passages and text generation capacity that they had, but it's actually being dwarfed right now, because some of the latest models are like 100 billion or 500 billion parameters, so getting into 1 trillion territory. And just for the context, I thought it's interesting that the human brain has around 100 trillion synapses, so the links between the neurons. So we're a couple more years, so we'll be in the human brain territory. Maybe 5 years. We'll see how it goes. But I guess one of the key lessons was that the performance of the models keeps growing, keeps improving with the size. And so BERT was down here, but BERT large is actually better than BERT, and GPT-3 is actually much better than GPT-2. Anyway, with that, let me go back to the BERT itself. So oops. Yeah, so it's a deep bidirectional transformer for language understanding. The article is called like that. So let me open the PDF itself. Okay. So it's not a long paper, but I thought just going through some of the key parts. So first of all, the BERT is a transformer model that creates token representations for any input text. Now, in contrast with what we saw last time, which was the classical transformer architecture, BERT is encoder only. So it doesn't have the decoder part. And let me go into onto page 13. Yeah. So
Dmitri,
can
are you intending to be sharing the PDF? We're still seeing the archive HTML.
oh, really? Okay, let me stop sharing and share again. Okay, can you see it now? Yep. Okay. So let me close this. Yeah, so this is the BERT, this is the GPT, and this is Elmo, another model which is not transformer. But the key distinction here is that BERT cannot generate new text. So BERT would take whatever the input tokens are and generate sequentially higher order representations of the input text, and then end up with some representation at the end. And at each step along the way, each token can look at all other tokens, to the left and to the right. And so this is why it's called bidirectional. So this is the first letter in BERT. Now, in contrast with that, both the classical architecture that we saw with Portuguese to English and, for example, GPT architecture is actually does have a decoder part. And so OpenAI GPT does not have the encoder at all. It's only the decoder. There are some that have both the encoder and decoder, like for example T5 from Google. But so those that have decoder part can generate new text and can generate basically new sequences. BERT cannot. And so I think that this is a key distinction. I would actually be grateful if someone told me that 2 years ago. So BERT, with this is a wonderful model. It achieved 5 points, etc. Improvements on most of the NLP tasks, apart from those that require generation, such as, for example, machine translation. So BERT would not be the right model for machine translation type tasks. Now, another thing I guess that needs to be mentioned is that BERT is both a pre-trained model, and so it can basically be used as is, and it can be fine-tuned, up-trained for specific tasks. And so, for many simpler tasks, such as classify IMDb reviews into good, bad, and mediocre, we could use just the existing BERT, which is more than enough for those types of simple tasks. Or if we have something like, for example, find the right answer for me from this Wikipedia article given the question. So this is more like a question answering type of problem. Then it will be highly dependent on the specific corpus that we need to train, and then we need to fine tune it. Now, the pre-training is done for many days. I believe they say something like 4 days on multiple TPUs, etc., etc. Fine tuning is fast. It's like we can do it within an hour. And so the bulk of the training goes into the pre-training of that base part. Now, let's talk a little about the structure of the BERT input. We'll get to this picture later. And so, yeah, here we are. So each BERT input is broken down into 2 sequences or sentences, as they call it. And so this is the sentence A and sentence B. And now I'll go a little into details why they have 2 sentences, but for now, basically they add 3 tokens, 3 auxiliary tokens, which is the CLS, the classification token, and then the 2 separators, separator 1, separator 2, and then so basically, they would encode each of these sentences through like 3 because they will have 3 components into each of the encoding. Now, first, the token embedding, which is the usual embedding in the token space, in the word space, and then the segment embedding, which meaning it's either the first sentence or the second sentence. This is the EA-EB here. And then the positional works exactly the same way as we saw last time. So this is a combination, a function that takes into account the position in the sentence and position along the model dimension. And so each of these, basically these 3 additives get together and provide the input embedding. Then going from there into the next level, and then the next level, and then 12 levels up into the output is done exactly in the same way as we discussed last time with the transformer. So it's self-attention only, and the masking is only done for the missing tokens, not for the causal, no triangular max, nothing like that, because this is a fully transparent model. It can look both to the left and to the right. And so at the end, we generate the output, which is trained so on a basically specific 2 tasks. Now there.
Can I ask something before you go here?
Sure.
These 3 embeddings that you shared, Dmitri, I assume the first one is learned and the other 2 are kind of derived from the input?
Yes, so the token embeddings are learned along the way, and then the segment embedding is just 0 or 1 to be specific. Okay. Like EA is 0 and EB is 1 always, and positional embedding is exactly the same deterministic function that we had. So only these token embeddings are learned. Yeah.
Right. Thank you.
So they have this layered structure which is probably not visible. But so what I want to say is, there are many layers, many sequential layers of BERT encoding going along the way until the output. And the output is, so let's break it down into two ways, into two components. So the first is next sentence prediction, NSP, and the second is mask LM. And so let's start with the mask LM. Is basically trying to recreate the input sentence from this BERT procedure, but at the onset, in the beginning, we mask 15% of the tokens, and so 15% of the tokens will be replaced, or are replaced in the BERT training procedure, are replaced with like a mask token, or are replaced 80% of the times, or are replaced with a random other token from the corpus 10% of the times, or are left intact actually. And so, but roughly, so 15% of the times, the model doesn't know which words are being masked, and so the task that it's actually solving and training along the way is predicting the mask tokens from the neighbors, from the context. And so that's why it's sort of thought to have, at least at that time, the best possible representation in terms of the language model itself. Like, what are the general probability distributions that you would look at your left and then your right and determine which token you have in the middle. And so that is the mask language model. The another good part and the efficient part about the mask language model is that it's self-supervised, right? So you don't need to have like a labeled corpus or anything. You can just take whatever corpus you have. They use 3.3 billion corpus, 3.3 tokens, billion tokens, and so they, during the training, they mask, like basically eliminate or mask randomly 15% of that and try to recreate, predict, the same thing. So doesn't need any human supervision here. So this is task number one, and obviously all the gradients are flowing back from the ground truth, as you would do with any type of NLP task. And so another source of gradients is the next sentence prediction. So many of the NLP tasks, at least the BERT was built to solve, involve two types of inputs, or two components of the inputs, such as like sentence one, sentence two, determine whether they are semantically equivalent or not, or sentence one, sentence two, determine whether sentence two is contradicting sentence one, or being the conclusion of sentence one, or is unrelated to sentence one, right? It's the entailment task. And so for those types of things, so the language model itself does give you the embeddings of the tokens, and so it represents the input. It could represent perfectly the input itself, so each token in the input, but it doesn't tell you the relationship between the two parts. And so for that, they have this next sentence prediction token, I would say. So this is the C. And basically what they did is they took the entire corpus and they split it into 50% the passages, the sentences will come one after the other. And so for that, the next sentence prediction token would be 1. And for the other 50%, those would be like randomly selected sentences for which the next sentence prediction would be 0. And so those would be different. And so the model was trained to recognize which sentences came from the same context and which didn't. And so this was the training procedure. It, as I said, it was ran for about 4 days for both BERT small and BERT large. It's just the size of the TPU clusters were different. So this is the training of the basic BERT, which is called the pre-training, right? The training without having any downstream task in mind. Now, after they had this, they up-trained or fine-tuned it on a few natural language tasks and achieved like remarkable results, more than 10, sometimes 15 points, improvement over the next available engine. So let me quickly go into a few tasks, and then we'll look at the.
So just to clarify, Dmitri, if I understood correctly, the pre-training is done on completely as a very simple task. If the two sentences are and belong to each other, like if there's a connection there, any kind of connection, that NSP equals 0 or 1, right?
Yeah, so NSP 0, 1, it's only for the pre-training, is only checking whether they are from, basically coming next to each other or not. So that's the only thing they check.
Right. And they could be supportive, they could be contradictory, they could be anything, right? That's where the fine-tuning comes into place.
Yeah. So that is before fine-tuning. Yeah. So all of those different types of labels come after fine-tuning. Yeah, this is just a quick example of how this works. Like for natural language entailment, and then Quora question pairs is trying to see if the questions are asking the same thing or not. Microsoft paraphrase corpus is also like whether the two sentences, whether the right sentence is paraphrasing the left sentence, etc. So all of these have basically a 0, 1 sort of binary class. And after we have the pre-trained BERT, we just up-train it or fine-tune it on specific corpus that we were interested in. And this is how it works. Now, yeah, this is the sentence pair classification. We can also do just one sentence. So without this separation, and there is a way to let BERT know that we don't need the second part. We just need to classify the one thing. I actually tried running BERT on Cola, which is trying to predict whether the sentence is grammatically correct or not. And so this is also a binary 0, 1 thing. So like this is slightly more involved. The squad question answering task, we will basically have, I remember when I said, we can generate new text, but given a sufficiently large text when where the answer is potentially present, you could ask BERT to identify the span, which is the beginning and the end pointers to the answer. And so you would have the question, and then like some short question, and then a Wikipedia article that probably has the answer, but we don't know where the answer is. And so that is exactly what Squad does. And BERT could be used to, fine-tuned version of the BERT can be used to predict the start and the end span. And so those tokens would have, a pronounced sort of dot product with the vectors that we will train. So basically, when we train, we know when the start and the end is, and so those vectors will be 1s and then everything else will be 0. And so the BERT will be fine-tuned to recognize, the correct positions of the start and the end. And finally, this is named entity recognition task. So each token can be, classified into a few categories, like a person or organization or a geographical location, etc. And so the output tokens are again compared to the ground truth, which has those labels, and the model is fine-tuned or up-trained through the gradients flowing from the actual NER tokens down the whole model. And so as we see, it's basically amenable to all kinds of anything that does not involve generating truly new text. Is BERT is really powerful. One last thing I was going to mention is that BERT can function as just a feature extractor. So for all of these tasks, actually, you would make all of the weights trainable, and so you would allow your algorithm to modify the pre-trained basic BERT's weights, but that is not necessarily your final objective. If you're training for something relatively simple, and or with something that has a direct sort of correlation with the training task of the BERT itself, without fine-tuning, like for example determining whether the two sentences come from the same context or not, then you don't even need to retrain the whole BERT. The only thing you could do is add another like a shallow layer on top of BERT embeddings, and just train that shallow layer, and use BERT as just feature extractors. And so BERT would consume your input sentence or a couple sentences and produce the outputs, and then you would use those outputs as just extracted features. So
that distinction, Dmitri, the distinction question, is that like, is there like a hard threshold, like, or is that just subjective? Or when would you do just
I guess, yeah,
few layer training versus full layer training?
I guess there are a couple things. First, trial and error, and see which one works for you. Whether actually in the paper they compare just feature extraction with full up training for a few tasks, and feature extraction at that time worked better than most competitors fully up trained. So that's one. Second, it has to correspond, at least superficially, with the actual training procedure that they have, right? So for example, grammatically correct sentences was at least on the face value was never recognizing the grammatically correct sentences was never the objective of the BERT itself. And so you would have a separate corpus and probably a deep up training to actually teach it to recognize. But something, as I said, like determine whether they come from the same context, or actually understand or classify words in context. So basically use the token embeddings in context. I think those tasks might be very well, they may work without the training of the entire thing.
Got it. Thank you.
Yeah. So let's, in the interest of time, move into the TensorFlow Notebook. Let me stop sharing this and let's make sure.
And for those of you who just joined us, this is the second part of the Transformer series. I'll post the link again on the chat. We have a recording of the previous series as well, which we highly encourage you to check out.
Okay, so yeah, this is the this is a notebook on the TensorFlow website. So let me yeah. So in TensorFlow Text, the previous one we did is actually this one, translate text with transform models, and now we will be doing this text classification with BERT. There is a whole section on NLP with BERT actually down here, and so very interesting notebooks which I haven't gone through one by one, but these are really interesting ones. They use TPUs. They try to recreate the glue benchmarks, and so if we have time, maybe sometime we could actually touch on these ones too. But this is text classification with BERT. Now BERT has become so popular that TensorFlow Hub has a whole section on BERT and BERT-like models alone. And actually, let me make sure. No, I don't have it right now. But we could actually, let's quickly look at that.
There was a link on your notebook for TF Hub.
Oh yeah.
Yeah.
Okay, so TensorFlow Hub text. Okay, so I don't know what this is, but here is BERT. Electra is based on BERT. Experts BERT is fine-tuned versions of BERT on different specific tasks. Albert is a light BERT, a small version of BERT, etc. So there is quite some BERT varieties here, and if we click on BERT here, it will give us some maybe 15 or so models to choose from. So, this is the processing for usability. So, they differ by the size. And as you can see, like hidden dimension 768 is the the basic BERT, and then 124 and 812, if I'm not mistaken, is the number of multi-head attention heads. And so you could choose from among these models. This is the Chinese BERT. So there are small BERT models, etc. So a whole zoo of models to choose from, and we'll be working with the basic one, which is the uncased 768 dimension BERT, which already gives a wonderful performance. So yeah, so that's the notebook. So again, in the interest of time, let me go rather quickly through pre-processing steps. So we would need to install a few dependencies, TensorFlow Text and TF Models Official. This is not necessarily required. So from Official NLP, we will import a special version of the Atom Optimizer. I haven't tweaked this notebook. If needed, we could make it much simpler, but I just thought we just take it as it is and run through it. So basically, we import the TensorFlow itself, the hub, and the optimization, and then IMDb comes as a prepackaged again data set that has both the training and the test part separated, so that there is a just be careful not to import the unsupported type, which is like 50,000 50,000 articles that are not 50,000 movie reviews that are not marked one way or the other. But after doing that, after importing the IMDb, and let me make a step back. So IMDb is a IMDb movie review dataset, which has basically, in this case, it's two labels only, like good review or bad review. So 25,000 files belonging to two classes. So this is for training, and 25,000 belonging to two classes. This is for testing, and for validation, we separate 5,000 reviews for validation from the training, and basically we will use that validation set to evaluate how the training is going. So we can look at the specific reviews, like, for example, this Pandemonium is a horror movie that comes off more stupid than funny. The label is 0, and then great documentary about the lives of New York firefighters, etc. The label is 1, positive. So this is what we will be asked to predict. And of course, we could, I mean, this is a just a template. This is a simple task that could be trained much easily with very light things. But this is just for the sake of demonstrating how the BERT works. So they go, they explain a little all of these, different types of the BERT models that are present on the TF Hub, and then they have this visual element to help us select the relevant BERT model, and so we select the smallest one. Now, each BERT model in the BERT TF Hub comes with a pre-processing routine that was not there, I guess, a few months ago. They added that just as to take a off-the-shelf pre-processing that was done specifically for that type of model. Many of the steps are, could be shared across many different types of model, such as, tokenization, and then encoding, etc. But they basically made our lives easier. Just have this link wrapped into Keras layer. So basically, when you call hub.keras layer, and then you just call, you just mention that link in parentheses, it will create a preprocessing layer that would take the raw input and produce fully inputs that are fully suitable for BERT ingestion, which have the token embedding, the segment positioning, etc. So all of the components that we need, and the input mask. So yeah, let's look at actually what is present in the preprocessed text. And so the keys are here. So basically, text preprocessed returns a dictionary, which is the input word IDs, masks, and input type IDs. Type IDs is the segment, is 0 or 1, and and it will be 0. Yeah. So we have, this is such an amazing movie as an input, and the output is so the word IDs is this one, and so in this case we limited the sequence length to 128, and so all of the zeros means that we just don't have tokens for those positions. So This is the input sequence. This is the input mask, as we saw in the last notebooks too. So basically, whenever we have a token, we will have 1, and we'll have 0 otherwise. And then the input type IDs is the segment ID. As I said, this is the first sentence and the only sentence actually.
So one thing, Dmitri, to be aware of, I've seen this many times with the trade-off of pre-processing as part of the model versus pre-processing like the data one time ahead of time before you even get to the model, is it will call these every time the batch goes through, right? So every epoch it goes back and does this again and again and again, right?
Yeah.
So it will slow down your training possibly, but hopefully it's very fast and doesn't take that long. But
yeah, you're right.
But if I understood correctly, this is like a requirement, right? If you want to use BERT, you have to use this pre-processing layer.
No, you don't. Actually, this is the first time I have seen this packaged as a layer. So I've used BERT before, and what you would do is you would create just a regular dataset generator that would take the input and then process that into the shape you want. And I mean, I find that way a little more instructive, because then you learn what are the expected shapes for the BERT input. Because here all we do is we just use these two links. This is the model, this is the pre-processing, and I mean, unless you want to go very deep, you don't really need to. But yeah, it's not that educational, at least. So I prefer to go like from the raw inputs to the TensorFlow dataset or whatever format you want, but I understand how it's actually being built.
So is this like a more efficient way to do this, or like a recommended way to do this? I understand you can do it on your own. I understand you can pre-process the input and make it ready for BERT on your own.
I don't know the answer to the question now, George. So I don't know if this would slow you down or not. So we could try. We could play with this and decide for ourselves. But this is easier for sure. So you have the model and you have the pre-processing, and you just you don't take care of all of these steps. It just takes care of itself. In that way, I mean, all of that logic, the pre-processing logic, is abstracted away into just one function call. I mean, this is convenient, at least.
Would you say it's a response to Huggingface?
Could be. I don't know.
Their interface is very easy and clean.
Yeah.
Maybe that's what it is.
Dmitri, I have a different question on the. Can you remind us what we're looking at here? We have a sentence that's 6 words long, but we have 9 non-zero tokens. Is the first one the class token and the last one the separator?
Yeah. 101, 102 are the separator, and I'm not sure if they actually.
You might embed the exclamation point.
No, could be. So these two are definitely that, and this is maybe amazing split into 2 tokens. You know what? I'm thinking about the way to check this. Let me go down the notebook, and then we'll come back to this question. So yeah. No, I don't. They don't have it here. Anyway, so
Dmitri,
Yep.
I don't know if you
Sure.
want to do this, but you could just create a small cell and just embed amazing and see if it gets to those 2 tokens.
Yeah. Yeah. You're right. Thanks. So let's let me continue, and then we'll come back to this. So just as with the preprocessing, the BERT, the model itself is can be wrapped around inside the Keras layer, and so we will call this exactly the same way. And so just mention the HTTP link inside. Yeah, so basically we just could check what it loaded. So it loaded this handle. The shape is this one, and so this is the pooled output, which is the C token, right? So the first token which we actually care about. Because this is a classification task, we don't care about the token embeddings at the last output layer. All we care about is this C, is this pooled output token. And so then we'll be, we could use this as, feature extractor, as I said, and have a small, a small layer on top of this 512, converting 512 into yes, no, into 0, 1. So this is actually what we care about. And this is we get as a collateral output, which we don't use in this case. And so these are the token embeddings themselves. So the sequence output shape is again the same. So this is the sequence, and this is the model itself. Yeah, so let me see if text set. Yeah, so because the text preprocessed is just 1, so there is no dimension. That is the 1 here. So just 1 element in the batch dimension 2. So, but generally speaking, you would have here the batch dimension, the sequence dimension, and the D model, which is 512 in this case. Here they explain, the 3 types of outputs that they get from the model, which is the pooled, again, the classification token, and then the sequence, and then the encoder outputs is the intermediate activations of the transformer blocks. And so, we won't need any of this except the pooled output for this thing. Now the model itself needs to be built with both the preprocessing, the BERT itself, and then the binary classification part. And so as always, it starts with the input layer, and here we have the inputs, right? So this is the input layer, which is capable of ingesting any type of text, and then preprocessing is the Keras, the TF hub preprocessing wrapped into Keras, and then the encoded inputs is basically calling this layer onto the text input, and then the encoder is calling the Keras layer again one more time on this thing, right? And we finally produce the outputs, which is the encoder layer processed the encoder inputs. And so here we have the outputs are dictionary, as we saw, and so the pooled output is just one, one type of the output, but this is the only output that we need. And then we apply the dropout, and then we apply the final dense layer just to give us the classification. Now they don't have the sigmoid activation here. They just have the linear dense. They chose it, to make it this way. This is fine because later in the model itself, in the loss function, I should say, the binary cross entropy has this flag, which is from logits equals true, and so they're fine with having just the the linear activation. If we I guess this is not the default behavior. So default from logits is false, and for the standard sort of the typical model, you would see from logits is false. So the binary cross entropy compares the the final sort of the final probabilities, not the logits. And so in that case, we would have the activation equals sigmoid here, not none. But they choose it to this way, which is fine. And so the classifier model is basically calling this build classifier function. And so we will see what happens just if the computational graph is working. Just the calling this thing on the on some test text, which is defined somewhere above. But yeah, the output gives us some probability. So this is the probability that the text is the review is positive. And so we can visualize the architecture of the model with this plot model thing from the Keras utils. And as we saw, because the BERT is wrapped inside the Keras layer, this entire complex structure is just one Keras layer, which is called BERT encoder. And so what we have is input preprocessing, BERT encoder, dropout, and then the classifier dense. So this is a very, very super convenient and super easy. So we then define the loss function, and the metrics is the binary accuracy, and train it for 5 epochs. So one thing to mention here is this thing, which I also don't know when they introduced this, but it seemed to be really handy. So you could actually call this TF data experimental cardinality to understand the size of your data set. So how many samples are there? Before it was not possible because the data set itself is a generator, right? And so you sometimes you would go into all kinds of non-standard ways to understand how many training examples you have. Now they introduce this cardinality, which makes our lives really easy. Yeah, so the only reason why they need this is because they create this optimization schedule that needs some understanding of for how many epochs are you going to train, and then separate part of that for warm up. And so again, this can be done in a much more controlled way. This is calling exactly this module from TF nightly. I think so, but even without that, this can be recreated using more regular standard tools. Anyway, now that we have this, so we compile the model and we train it for 5 epochs, just a regular training procedure with .fit, and we have this validation data. We don't have the early stopping or anything like that. It's just, you know, training for 5 straight epochs. Yeah, so
Can I ask something, Dmitri? Are you training
Sure.
the entire BERT model or just the dense layer on top of it?
No, the entire day, the layer.
Okay, perfect.
Yeah. They have a flag for that, George. When you call it, they have a flag. I'll look where it is. So you mentioned it specifically, whether you want to train it or not.
It's the hub layer where you load the encoder. There's a
Probably.
training. Yeah.
Yeah. Let's well, let me find it actually. So somewhere here we mentioned trainable equals yeah, here. So we could do actually that. It would be interesting to compare trainable equals false and have everything else the same, because you would still train, you know, this guy, right? So mapping from 512 to this one would be still trainable. So yeah, so they visualize the training history, again as usual with the history object, and then, you know, it doesn't tell us much, or you know, it's rather telling us that even in the second epoch it's already training with the 85% accuracy, and it doesn't improve any longer. So it doesn't make sense to train for longer. So I guess, you know, we could play with the warm up and the learning rate, and make this look more normal, as you would expect, like, you know, growing for at least a few starting epochs and then starting to decline, etc. But, you know, for the purpose of quick demonstration, I think this is great. Yeah, and then what they do is, you know, they demonstrate how you could export it or save it as a saved model. And this is I believe, yeah, this is a new syntax. So saved model, as in TensorFlow saved model version, as opposed to the older Keras models. And then for some reason they test whether the reloaded model from the saved model actually produces the same result, which of course it does. It's done in the same notebook. And so they have a few sentences, and, you know, we could try to see what the model produces. So, you know, clear markers here: amazing, great, terrible. So when the clear markers are present, you know, it sort of works perfectly. Okayish, perfectly. 0.3. Meh, it didn't recognize. It thought, you know, it's a good word, but I guess it's the other way around. So yeah, and we could try just, you know, input any other sentences. Let's see. Actually, you know, let's see if you input something neutral like this. Oh, 0.4. Okay. Anyway, so yeah, we're not exactly sure what this is. So yeah, that was the notebook. So please let me know if there are any questions. There's been some discussion in the chat, right?
Yeah, thank you, Dmitri. Yeah, we were chatting about the 999. It's actually the exclamation mark, as Christine said, the token for that specific ID.
Okay.
And the sigmoid, that there should be a sigmoid at some point, otherwise you're just looking at random numbers. So there was a sigmoid when you were printing the output there. Yeah, I don't know why they did this way. Was it faster to train, or?
I don't know. I don't know.
I haven't seen
So
it before.
Let me just double check this. So TF Keras, binary cross entropy. Yeah, from logits is false. Yeah, the default behavior is false. For some reason, I don't know.
Right. And I might have missed this, but this cardinality, you needed it just to get an idea of the scope of the scale of the data set. That was the only reason?
Yeah, well, in the past it was so there are cases when you need to know the size of your data set without actually maybe it came from somewhere else, or it's a generator, right? So you're not always sure how many training examples are there, and so there is no easy way to check it unless you go to the source data and do the calculation yourself, like divided by the batches and all of that. And so they introduced this cardinality function, which can just ingest the training data set and produce the steps per epoch. Or I should say, the number of training examples. I'm not exactly sure whether they actually sort of, instantiate that in memory. I don't believe so, because that would be a stupid thing to do. So the data set itself is maybe a generator of huge amounts of data. So how exactly they find out the number of training examples, I'm not sure, but they have this function.
Okay, interesting. Any more questions, friends, comments?
Okay.
Hey, George.
Yeah.
Regarding the binary cross entropy, I've seen that before. I can't remember the details, but I think that there's like an exponent in the logit function, and when you do the loss as a log loss, it sort of cancels out the exponent, and so it saves you computation if you don't actually calculate the logit. I don't remember the exact details, but basically it's just you definitely could do it, but there's less math if you don't do it.
But we are calculating it here, right? It says from logits true.
From logits true means that you're not taking the logarithm. You're just
you're
an
not.
argument that would be sent to the log.
Got it. Okay. So maybe it's like a numerical shortcut.
Yeah. Yeah, you're just skipping doing an extra whatever log, which then when you do the loss function, it gets duplicated or whatever.
Right. Cool. Thank you, Ted. I hadn't come across it. Christine has a question about the token embeddings, the segmentation embedding, and the position embedding. Are they the same for? Are they the same as the one we looked at the paper, or? So transformer is a generic term, yeah.
So positional encodings are the same as we saw. So the segments embedding is a very BERT specific thing. You don't see segment embedding apart from.
Okay.
So segments embedding is specifically to distinguish between the first part and the second part. And the token embeddings, actually BERT trained its own BERT embeddings as opposed to using something else. So they would be specific to the BERT model.
Hey, Dmitri. The embedding vectors are trained by BERT, but it's using a very similar word piece, type encoding that lots of other models are using.
Yeah. So the tokenization is not BERT specific. The vectors are BERT specific. Yeah. And
so 5
I guess they
epochs
have something like 30 something thousand tokens at all. So which is not a big number.
But the takeaway for me is that just with like 2 or 3 epochs, you already reached a good number in terms of accuracy there for this data set. Like it was a relatively easy task for BERT to accomplish this sentiment analysis.
Oh yeah, this is like very easy for BERT, I guess. So I've tried BERT in a number of contexts. The corpus of linguistic acceptability was one that was actually tricky. And yeah, you wouldn't do like 5 epochs. It would train for hours until it got to acceptable level. So
is that a grammatical error check?
Yeah, grammatical correctness check. Yeah.
Okay.
And there are all kinds of like very subtle mistakes made in the corpus, like the the antecedent is wrong, and like one letter S may turn you off, etc., etc. So compared to this, like amazing is good and terrible is bad. It's like very easy to
yeah,
make sense.
I would imagine the squad test, right, with a question and answer, trying to find the answer within the paragraph. I think that would be computationally intensive.
Which one? Say it again.
The question answer one.
Oh, the squad. Yeah.
Yeah.
That's intensive. Yeah.
Hi, did you mention that there's only 30,000 tokens?
Yeah, 30,000 word piece.
The word
tokens.
embedding?
Yeah. No, 30,000 types of tokens, right? So 32,000, if I'm not mistaken. So there is the standard byte pair encoding or word piece encoding, which for like frequent words, it treats them as separate tokens. For less frequent words, it tries to separate the token into 2 pieces, for example, that are frequent enough. But for like unknown words or like foreign words or some gibberish something, it would chop it off into individual symbols, like individual characters. And then all of that, because it has this flexibility, we don't have to memorize the 300,000 words that there are in the English language, because all of them get sort of packaged and then chopped if necessary to represent the entire population. I hope this makes sense.
Yes, then I guess it's different from the GLOVE.
Yeah.
400,000.
Yeah.
So the GLOVE one, that is just one type of word embedding.
Yeah, glove
in BERT, you have
is
many different types.
right. Yeah. No, glove is just one token to a vector, right? Like 200 or 300 long, etc. So byte pair is not one word, is one word or part of a word mapped to a vector. In this case, vectors are larger than in glove, right? So they're like 768 or 1024, etc. But regardless of the size of the vector, the objects they are mapped from are different. In glove, in word2vec, they're words. In this encoding, they are words or pieces.
Thank you.
Any more questions, anyone?
Dmitri, I had a question. Do you feel that if you continue to train a BERT model, that it will overfit, or it won't really hurt you, you're just wasting time if you keep training it longer?
On this particular task, Ted? Ted, you mean on this particular task, or?
Well, I guess maybe the answer is task specific, but yeah, let's just use this one as an example.
It can be done actually. Let's. I don't remember how long it trained, but let's see if the notebook is still active. So let's see. No, something went wrong. So so I guess I don't see any reason why it shouldn't overfit, like with any other very powerful model. We made it trainable. The entire BERT would train, would receive the same gradients and the same gradients all over again. And so I guess it would overfit. In this particular case, they don't have any guardrails, like no early stopping, nothing. So I believe it should deteriorate. But we could. I mean, there are a number of ways to protect against that. And I just don't think they spent a lot of time because of the nature of the problem thinking about the right learning rate and early stopping and all of the mechanisms that we know how to implement when needed.
Yeah, because Robert mentioned dropout, and a lot of these large models I've seen, there's enough regularization built in that people sometimes they just train these things forever. Like these large image classification models, they'll train them for eons of over and over and over.
Yeah, I once tried to train a chatbot using a transformer type architecture, and I mean, only the next day I figured that it works at all, like because in the first couple hours, or maybe in the first few hours, you don't see any change in your metric accuracy, perplexity, whatever you measure. It just stays flat. It just takes forever to warm up. And so in BERT, what they did actually, the paper discusses in fairly great detail how they approached training. And so it trained, for 4 days. They had a very, specific warm-up schedule, and then all of, I mean, there is all kinds of hyperparameter tuning that went, behind the curtains that we don't see. Yeah.
Cool. Thank you.
And I'd say the other thing that makes a case specific is how much noise do you have in your training data, right? So if it's going to really overfit and learn to train on that noise, then it's not going to generalize at all to your to your test set. So that's kind of I don't know about this data, but that's always something.
Thanks, David. So probably safer the more data you have, the more variety.
Cool. Just for completeness, do you mind chatting a little bit about the Huggingface library, because we wanted to quickly touch base upon that. So we saw TF model. Can we just quickly touch upon the Huggingface library and where does that fit into the picture?
Yeah, I'll be. Oops. I'll have to go in a couple of minutes, but so they do have all these wonderful libraries, and so I guess a couple things. First, they created very convenient wrappers around the when you import Huggingface, and then there is a wrapper for all of these, both for the TensorFlow and Pytorch. So yeah, the Huggingface itself is a startup that just closed round B. They do all kinds of natural language processing tasks. So the chatbots and you know, basically, but their reputation is with transform models. So maybe, you know, if we have time next time, we could start with actually looking at a couple of notebooks that implement Hugging Face libraries. But yeah, so this is a go-to place if you want to actually import something and to run under TensorFlow or Pytorch, unless there is a, you know, a TF Hub model already there. But TF Hub actually, as we saw, only had BERT and a few varieties of BERT. And so ROBERTA, for example, is a Facebook model. GPT is, of course, the OpenAI, and so forth. So for none of this, TensorFlow Hub is a good place. You would go to Huggingface.
So we have more variety. Got it.
Yeah.
What if you look at the same, let's say, BERT model in Huggingface and TensorFlow Hub? Would performance be the same, or the developer experience be the same?
I guess, I mean, Huggingface, because everything is open space, yeah, open source. They just imported from the, as far as I understand, that they imported from the GitHub, you know, the latest version, and they create a few API layers on top of it without changing much. But maybe maybe, you know, they do something else that I don't know.
When you say GitHub, you mean the paper GitHub?
No. The BERT sits somewhere in Google's GitHub, in TensorFlow GitHub, and so they imported from there. So yeah, it was and first released in this repo, so they have all of the input information must be here.
Got it. Cool. Thank you, Dmitri. I know you have to hop off. We really appreciate it.
Thanks, George.
Cool. Thank you so much. Awesome, friends. This was a fun session. Just want to share with you some upcoming adventures that we have, and then stop the recording, but I'll leave the floor open for discussion. So this concludes the second part of Transformers. There's another one coming up later in December that's more of an application based. It's actually a Kaggle competition that Dmitri participated. That's on December 1st here, using attention-based models on non-NLP tasks. This is like structured data. For the next couple of weeks, we have a happy hour just to give us a break to prepare for the next session, as well as get to know each other better and, you know, forge a stronger community. And after that, on November 10th, we will cover this new mini course that Kaggle just released a couple of days ago on time series. So check it out. It has standard statistical methods as well as machine learning based methods for modeling time series. So we'll be talking about that on November 10th. And then after that, we have something new and exciting. Now we're still trying to frame it well, and see how it fits our schedules. But yeah, that's a surprise for our community after November 10th. Yeah, that's what we have. And again, the recording will be posted on the DLA transformers bit.ly that I shared, where they have part 1 or 2. The second part, today's session, will be uploaded tomorrow. Cool. That's it. Thank you, friends. I really appreciate it. I'll stop the recording here, but I'll leave the session open. Again, thank you, Dmitri, for leading these 2 sessions that were really useful. And thank you, everyone, for participating with questions.
Okay, thanks. Thank you.
Thank you, friends.